So today we're talking about constraint satisfaction problems, and I have a special guest lecturer. My friend Kuldeep Meel teaches one of the other sections of 3600, and he has spent 15 years studying constraint satisfaction problems. So I begged him and I begged him and I begged him, and he said he would come and do this lecture and the next one for me. Actually, he owed me a favor.
Yes.
So here he is, and I'm going to sit and enjoy. And this is the moment my spring break starts.
Yeah. All right. Thanks a lot, Aaron, for letting me talk about it. So this is a topic.
It's a little loud. I'm sure you done.
Oh, okay.
Go ahead.
Yes. So this is a topic I have spent 15 years. So of course, I would have wanted to spend a semester teaching you all about it, but we had to do with just 2 lectures. Okay. I gave the same lecture yesterday in the section B where I'm teaching. So let's see. Okay, so what are we going to talk about? We are going to talk about another different approach to solving problems, which is called constraint satisfaction. We'll see why soon. And it starts with, if you think about a lot of issues that will arise with agents, is that we want them to take actions, but there are a constraint they must satisfy. So one of them is maybe you want an agent that has to figure out it's operating at a port and it has to fill the containers. So what it has to do is that the ship lands, and then subject to the ship's size, weight capacity, and delivery date, you have to figure out what content should go on the ship. The reason I'm talking about this problem, before moving to Georgia Tech, I used to be in Singapore. So I moved to Singapore, and one of the first people who came to meet me were people working in the Singapore port. And they wanted to see how we can optimize further. So this is a problem people really care about, and which is where the techniques that we are going to see today really get used. If you have gone around ATMs, someone has to figure out what kind of how much money should be in an ATM, what denomination should be in the ATM. There are constraints. There are physical constraints in terms of the number of currency one has. At the same time, you don't want to show up an ATM and find it's not able to dispense cash. But not everybody uses every ATM, so the banks have to figure out how to allocate money to different ATMs when they go around filling them. Similarly, for scheduling football games, everybody wants game at their own college for the homecoming weekend, but of course 2 teams have to play. So someone has to figure out how to schedule these games. For example, NFL uses one of these, something that we are going to see, the tools based on those ideas. There are travel constraints, broadcast windows, revenue requirements. So, and similarly, someone has to figure out what classroom should be given to what course. There are going to be enrollment projections, scheduling constraints, the time available for the faculty, and you also want to minimize conflicts among the students who possibly want to take these classes. So you can see that there are many such problem situations where you have a lot of constraint that we need to satisfy. So what can we do? Well, we have kind of already looked at one approach to solving these problems, and that approach is model everything this is a search problem. For example, you can say that I have a starting state. As you probably saw in case of traveling salesman, you have the ending state where you should have traveled all the possible cities, and you model this as a search problem. You have seen already what to do. If you model this as a search problem, we had to figure out how to define the state space. We had to also figure out what will be the domain-specific heuristics. Remember, A star worked really well because you could come up with a good heuristic. Probably that's also something you realize in your homework. If you don't have a good heuristic, these algorithms aren't going to work well. So what can go wrong in this approach?
Yeah. Something that has a lot of states, maybe too many.
But let's say we want to try this approach of modeling this as a search problem. So what we had to do? We had to come up with a heuristic. And we'll have to come up with a heuristic for each of these problems. So wouldn't it be nice if there was kind of an approach where you just model these problems and there's just one algorithm that figures out how to solve it, and you can do a separation of concerns. Your concern would be to model these problems, and then there would be a universal algorithm that would be able to solve all these problems. And this challenge that we are talking about is not just because there are many different problems you have to deal with. This also goes to like this same problem. So suppose let's go back to the traveling salesman. You looked at a very good heuristic, which was based on minimum spanning tree. Okay, but suppose I want to say that, look, I also would like to visit C10 before C9. And you have to visit C7 only after C5 and C6. Well, the heuristic that we had on minimum spanning tree will no longer work, right? Because it won't be able to satisfy these constraints. So even for one problem, if you slightly change the variant, you'll have to redesign the heuristics. So not only that, you have to come up with a heuristic for every new problem, you have to also keep redesigning every time the problem slightly changes. That's very unsatisfactory, because what you would want to do is that you would want to change the problem and let something else figure out how to solve it. And that's exactly what we are going to see, which is that how we can have a method where you can encode everything and let the computer figure out. So what we want to do is that we would like to specify what we want. And then there's an algorithm that should figure out how to solve it. And we are going to look at both the aspects. We'll see how to specify what we want. This is also what you are going to do in your homework. And then we have an algorithm. We are going to look at the algorithm that figure out how to solve it. Okay? So in particular, what we are going to look at this paradigm called constraint satisfaction problem. There are three characters here. There's a notion of variables. Each variable takes values from some domains, and then we have constraints over these variables. Okay? And what we are going to come up with is a general purpose algorithm, and one algorithm that is going to be able to handle every problem that you can cast in this way. Okay? Something where you can specify variables, constraints, and variables, their domain, and the constraints. And again, the key here, why it's a big deal, is that because it allows you to just focus on two aspects separately. Someone designs the algorithm, and you only focus on how to specify what should hold. So no matter your different problem, you'll be able to use the same tool. In some ways, this is reflective of how computer science has evolved. If you think about, at the end of the day, your computer is just a circuit that is outputting zeros and ones. And we figure out what problems we want. We encode those problems to the computer, we read out the zeros and ones, and we are able to interpret the solutions. So this is similar to what we want to do, but on a level of solving these special class of problems. Okay, so we talked about that constraint satisfaction problems have three components. There are going to be variables, domains, and so we are going to use one notation where we have a set of variables which are x1 to xn. Okay, just so that we have some way of talking about them. And it's a set of the variables here. Each of the variables can take their own domain. Often we are going to look at the case where maybe all the variables take the same domain, but you can have different domain for each of the variables. And what is a constraint? A constraint is something that takes a subset of the variables and restricts what are the values those variables can take. So a constraint can look like, yes, some variables, and you could have a constraint that says x1 plus x2 greater than equals to 3. Okay, so this is talking about all the cases where x1 and x2 must be greater than 3. So over some subset of the variables, we have put some restrictions on what values x1 and x2 can take. So the way to view constraint is that this tells you all the tuples of the values that are being restricted. So the variables must satisfy this. So every time x1 and x2 must take if the values where x1 plus x2 is greater than equals to 3. Okay. The way, how do you specify these constraints? Well, we are going to look at few ideas, but one way to think about it is that you can just think like somebody just gave you a table where you specify what are all the values of x1 and x2 that hold, for which this constraint holds true. Okay. And what do we want to do? We would like to figure out some assignment to all these variables so that the constraint holds true. Okay. And this is such an assignment is often called a solution. So often we'll say that, can you find a solution to these problems? So you can see that satisfying this constraint, this is why we call it constraint satisfaction as the area. What are variables? Of course, these are the things that we would like to determine. In case of maybe in case of a course, we would like to figure out what time should be assigned to the course, or what should be the denomination put in the machine. What city you should visit at the step I of the tour. Okay, so this is what the variables are going to look like. We are going to, for this class today and in the assignment, we are going to look at two particular domains. One is the integers, so where the variables can take integer values. The second is when the variables take value 0 or 1. You might think like 0 or 1 might be too restrictive. It turns out that specifying constraints on variable that take 0 or 1 is a very hard problem. In fact, this is a problem for which we do not know if there is a polynomial time algorithm. This is a very famous problem called Boolean satisfiability. If you can solve it, there are $1 million waiting for you. So this is so you can specify entire constraint satisfaction problem over variable that just takes values 0 or 1. Okay, so of course we are going to talk about something that is so powerful that can, for which we also do not know an efficient algorithm in the worst case. But don't worry, we are going to look at an algorithm that's going to work well in lots of practical cases. So we already talked about what are constraints. Well, just to formalize, a constraint is over a scope. We call it a scope, which is the subset of the variables over which the constraint is specified. You can think of a constraint mapping every assignment to true or false. Okay. So I'm going to keep coming back to this problem that's based on n queens. So how many of you have seen a chessboard? All right. So you see on the chessboard, if I want to place n 4 queens, so I'm going to draw a smaller chessboard, right? 4 cross 4. What does a queen do? A queen can attack other queens if it's in the same row or along the same column or along the same diagonal, right? So you could specify that, look, I would like to place queens so they should not attack each other. And then saying that when the two queens don't attack each other, you could specify the location of these queens and describe when they attack or not. Okay? We are going to soon see a complete example for it. So this is kind of what the constraint look like. You have variables and you tell that, look, if these are the values these variables take, then the constraint is true or false. Okay, so let's try to encode this problem. So if you want to place n queens, then we have variables x1 to xn, the domain. So let's figure out the entire problem for 4 queen. So what should be the variables we have? For 4 queen, how many variables do you think we should need? 8 variables that are about xy% of each queen. Can we do with less than 8 variables? Or so we can also use, when it comes to encoding the problem, we can use some information about the domain, right? And so one is, we know that, look, for the problem we are trying to solve, you can't place two queens in the same column. So we are just going to figure out in each of the row where the queen will be placed. Okay, so we can say that the x1 is the variable that tells where the queen gets placed in the first column. Okay. So now that we have this variable, we have to figure out where the queen gets placed, how many values it can take. 4 values, right? Each of the rows it can place. What about, how do we specify the constraint that the queens should not attack each other? We looked at one view, which is to specify the table. You could also try to specify things writing, the way we write in math, some equations. Can you think about how can we specify what does it mean for two queens not to attack each other? So what would it mean for queen in the first column and second column not to attack each other? Sorry? So a constraint is over a set of variables. Yeah. Sorry? You said the constraints like the valid points for. Yes. So we know that all of these can take values between 1 to 4, right? Now we want to say, what does it mean for x1 and x2 not to attack each other? So one way is that we could just specify a table, right? We could say that, look, let me tell you all the values when they don't attack each other. For example, when x1 is 1, x2 will not attack if it is placed in the location 3 or 4, right? And so on. Is there a different way? So what we know is that the value of x1 and x2 should differ at least by 1. Right? So that's a constraint. It's a constraint that is talking about these variables. You can specify using tables, you can specify using these equations, right? Is this clear? What is a constraint? A constraint takes a subset of variables and captures the relationship between those variables. It tells, once you look at a constraint, you assign the variables, then you would be able to look at the assignment of variables and see whether the constraint is holds true or not. If it's an equation, then it means that the value of x1 and x2 should be so that if I take the absolute value, it must be greater than 1. Okay? All right. And of course, once something returns a solution, then we'll know where to place these queens. Okay? So I put out this the handout of the slides, but I took out one slide from that handout so that there is something for you to do in the class. So suppose we want to place 6 knights on a chessboard so that they don't attack each other. Okay, let's talk about, as you can probably guess, I don't have a good way of drawing, so I'm just going to use letters, okay? So when can a knight attack another knight? Let me brush you up on your... So if 2 knights are over something like here, then they can attack each other, right? So we want to place 6 knights so that they don't attack each other. So how many variables do we need? Can you have 2 nights in the same row? Yeah. Sorry? 12. Can we do with less than 12? Yeah. 6? What are they going to tell us? Yeah. Any other ideas? You are on the right path. We can do with 6, but how are we going to encode? Yes. Exactly. We can give each of these cells some number, right? 1, 2, 3, 4, 5, 6, 7, 8, 9. And then we can say, okay, let me figure out where should the night 1 go to. So each of the xi variables are going to now take a value between 1 to 16. So what can x1 can represent the position of night 1 and so on, and x6 will represent the position of night 6, right? And now we can say that, look, when will x1 and x2 attack each other? Well, they will attack each other if x1 is at 1 and x2 is at 10, right? And none of the variables can take the same value as well, right? You don't want to place 2 nights in the same cell. So this is one aspect that does require work. You have to figure out how to model the problem. We are not taking away the entire difficulty. You have to figure out how to model the problem. And the thing with this constraint satisfaction is that once someone tells you the model problem, then it always looks like, of course, what else would you have done? The hard part is figuring out how to model these problems. And you are going to get a bit of quite a bit of exercise in your homework. Okay. All right. And then finally, you have to again write something like this, that you don't want nights to attack each other. Okay. Okay, let's go back to the traveling salesman problem. So suppose first we just want to make sure that we are able to travel all the cities. So how would we model this problem? You have n cities, and let's say you can go from anywhere to anywhere. Okay. So let me help you out. Let's say we are going to have variables where pi will tell us the position of the city I in the tour. Yeah. If they are all different. Yeah, exactly. So what you have to say is that, look, all of them have to be different. So let's not worry about it coming back. So for a minute, then we are going to say that, look, all of them have to be different. So that's the constraint. How can you say that all of them are different? How do you write it? The length of the path is this. Okay, let's see. So remember, pi encodes the position of the city I. So let's say there are 4 cities. So maybe we can say that P1 plus P2 plus P3 plus P4 is, there are 4 cities. So how do we specify that all of them are different? So one is maybe the sum of them have to be equal to. Is that what you were on? Okay, so let's see what else can we do. Yeah. No. So what can we do here with P1 and P2? They should not be equal to each other. So we are just going to write this constraint that says that, look, they should not be equal to each other. In some sense, it is kind of very nice. You had all this, the entire problem, and all we had to write is just these constraints, right? And let's go back to this thing that was kind of troubling us, that C10 should come before C9. Well, all we had to say that, look, P10 should be before P9. We had this issue that, look, uh, we wanted to say that C7 should come after C5 and C6. Well, P5 should be greater than C5 and P5, sorry. We can just say that P7 should be greater than P5 and P7 should also be greater than P6. Right? So in some ways, it is just amazing that you can just write this constraint simply and let someone else solve it. Sometimes there are constraints that you are kind of okay with not being satisfied, but ideally you would like to be satisfied. And that's what, in case of trailing salesman problem, you want to minimize the length of the tour. Right? So these are called soft constraints. And these encode our preferences. So, in case of trailing salesman problem, we want to say that, look, the length of the tour should be minimized. And then this is where we can use minimize or maximize. So these problems are called optimization problems, where you also specify an additional objective. Okay. In this lecture, we are going to focus on feasibility, on the cases where we want one assignment that satisfies all of them. Okay, so one thing that we have been looking at is that we are looking at these constraints, conjunctions, that all the constraints must be satisfied. You might say that, look, maybe I have some problems where I'm okay with one of the two constraints being not satisfied. Okay. What I want is that either C1 should be satisfied or C2 should be satisfied. How can we encode that problem in our framework? So we can come up with another constraint that takes the or of the two, right? What can go wrong with this approach? You remember, every time you say or of the things, you increase the scope of the constraints, right? The number of variables keep growing. So if you were specifying things as a table, then the tables will start becoming larger and larger. Is there a different possible approach? So let's try to see if we can have such an approach. And then I'm going to come back to this n queen problem, but now let's say that we want to place 5 queens. So if we want to place 5 queens, how many variables we need? 5, right? But of course, the 5 queens are going to attack each other. So let's say that we are okay with if at most 5 pairs of the queens attack each other. So how can we specify this problem? What do we do? Sorry? So in some sense, we will be just going over all possible solutions then, right? And that kind of defeats the purpose of what we are doing. We wanted someone else to take care of solving the problem for us. And this is for a small example of 4 cross 4. Let's say the chessboard was 100 cross 100. And we were okay with 5,000 pairs to attack each other. So we'll have a gigantic table to specify, right? And worse, we are already solving the problem. Is there a different way? That does not require us to write a constraint that is over all the variables in one go. Do you see the problem? If we start writing this, then if n grows larger and larger, we'll have to write a huge constraint that talks about all the queen and then say, okay, when in what rows it is okay, if at most 5 of them attack or not. So this is one of the simple ideas that have been rediscovered many times. In every community that uses constraints, people get stuck on a problem like this, spend few years, and then somebody discovers, and then everybody like, oh wow. And then a year later, everyone like, well, what was the big deal? This is such a simple idea. So let's try to see. So here's the idea. We are going to say that, look, we'll introduce an extra variable for every pair of queens. So we are going to say that, look, when A12 is 1, then it implies that the queens are attacking each other. Okay? We can also write it the other way, which is to say that if A12 is 0, then this implies that they are not attacking each other. Okay? And we are going to write these constraints for every pair of xij. So we are going to have okay? We had to anyway write constraint for every pair. So this is just going to be the same number of constraints we are writing. Okay, just an extra variable, just one extra variable. And then we need something more. Sum of these aij should be less than equals to 5. Yeah, so that's a good point. So here we can ensure that we are only writing x12 and not writing x21. Okay? So that depends on what we define as a pair. Okay? Okay, so this is kind of the really core idea. A very simple idea, takes a while to internalize. So the idea is that you want to come up with a new constraint, which is encoding this idea. And the thing is that you can also write this constraint in the following way. You can say that, look, when aij is 0, in that case, I definitely want the queens not to attack each other. I don't care what happens when aij is 1. But if you are going to make sure that only at most 5 of them can be assigned 1, then everything else will be assigned 0. So this would ensure that only at most 5 of them attack each other. Okay? And in the solver that you are going to use, this is where this constraint appears. So you want to say that, look, I want to add a constraint that don't attack each other, but you have to enforce it only when aij is 0. And as I talked about, so this is the idea of introducing extra variables. So if we think about, for us to read the solution of this problem, we didn't have to really know the assignment of these Aij, right? Because Xi's are encoding the location of each queen. So we are kind of introducing an extra variable that was not in the description of the problem. And that's where the entire power comes. Being able to introduce extra variables that don't appear in the description of the problem. Okay. And this is something you are, of course, going to look in your homework. You have to figure out what extra variable to introduce so that magically you'll be able to encode the problem. Okay. All right. So far what we have seen is that how to specify these problems. Well, somebody has to figure out how to solve them also. So let's try to look at the algorithm that powers all the solvers out there. Okay, so the core algorithm. And we are going to look at that algorithm in two parts. Some of the parts we are going to look today and rest of it in the next, the week after spring break. So look, even for this n-queen problem, the space of all possible assignment is fairly large. So you can imagine that if you wanted to solve like 8-queen or 16-queen problem, this would be very large space. So we can't just go over every possible assignment and try to see. So we do need some smart idea here. So maybe one thing we could do is we assign every variable some value and we check if the assignment satisfies all the constraints. As you can guess that that's probably not going to work very well, right? Because you'll go over every possible assignments and the set of possible assignments is too large. But let's try to at least see how that algorithm would look like. So what we are going to do is that we are going to check if all the variables are assigned. And in that case, we'll return the assignment. And what we want to do is that we have to figure out what variable to pick. And then we have to figure out what value to assign. And this is where a lot of solvers, there's a lot of time and effort spent by solver developers who design heuristics on what variable to pick, what value to pick. And then, of course, we can just, we have to maintain some data structure. So we are going to maintain this assigned data structure that contains things like variable equal to value. Later on, we'll also see that sometimes it's also helpful to say that variable does not equal to some value. Okay. And you can just recursively call this backtracking. And if you fail on all possibilities, then you finally return failure, that it could not be satisfied. Okay. So let's try to see how this would look like. I have a demo on the n-queen problem. So what is this going to do here? Let me slow it down. It's trying to slowly place, and every time once it places all the queens, it discovers that, oh, it does not satisfy. What is wrong about this algorithm? Huh? It's too slow. But why is it so slow? Yeah. But what's kind of the fundamental weakness about it? Yeah.
I was gonna say it explores like paths that you already know, like prior.
It explores, yeah, look, for example, here. we already know that you can't place the first two queens in the same row. And it keeps us exploring things that are never going to work out. So what can we do to fix? We should stop immediately, right? So for example, let's go back to the settings. So we place the queen 1 here. And then when we are placing the queen 2, should we play, if we place the queen 2 here, does it even make sense to figure out where to place the third queen and fourth queen? No, right? We should immediately say that, look, some constraint is already getting violated. This is also called conflicted. Some constraint is not being satisfied. So we should backtrack immediately here, right? It makes no sense for us to try assignment to the other queens. So when we are assigning where to place the second queen, we should at least ensure that the placement of the second queen does not violate any constraint. The value we are taking immediately does not falsify any constraint. Right? So where can we, should we place the second queen over here? What about here? This does not violate. We don't know if it's okay or not, but at least it does not violate any constraint. What about the third queen? Can we place it here? 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 So what do we do now? We go back and we have to try the next value. Okay, so let's see. Is that the algorithm I have here? So we should make sure that we are picking some value that is consistent with the assignment so far. Okay? And once we have gone over all possibilities, we keep backtracking. So let's see if this is kind of smart. It did work much faster, right? In fact, we can now hope to solve maybe on a real chessboard. A real chessboard is of size 8 cross 8. So something that is important here is to figure out that all we are ensuring is that no existing with the value we are picking, it does not violate any of the constraints so far. It does not mean that that value is going to work out, right? We don't know what can happen in future. But we know that whatever value we want to pick for the variable we are assigning, it should not violate any of the constraints. Yes.
So like two sets of constraints. It's like the constraints which are kind of like a heuristic that like you search the state of space kind of quickly, and then there's the actual constraints like make sure they're not in the line of sight that takes longer to check and that's not as efficient, I guess.
No, we have only one set of constraint, the one that must be always satisfied, which is that all the no two queens should attack each other. Oh, that we can specify using just what it means for the two not to attack each other, right? Okay, so in case you are thinking, how come it's so slow? It's because I've been showing the trace. Let's try to see. Takes few milliseconds to solve this problem. In fact, how many of you like solving Sudoku? All right, so let's see. In the other section, I even gave this as a homework exercise, so you should not tell them, not as a homework, but as a spring break. So this is kind of mildly hard Sudoku to solve, okay? In fact, I'm just going to display the solution and then send an email for you to try out on your own. Let's see the algorithm that we just saw. How fast can it solve? "47 milliseconds. If you don't have a spring break plan, this will be a good way to spend your spring break. It should take you a while. So these algorithms are really powerful. Once you figure out this algorithm, it's hard to kind of sit down and try to solve Sudoku on your own, right? You might as well just code up this algorithm. Okay, any questions about this algorithm that we have seen? This is fairly powerful algorithm that works a lot of times. Okay, so let's go back to the demo we were having. So in this, so when we are trying to implement this naive algorithm, the number of assignments it tried was 154. When we implemented this improved algorithm, the number of assignments it tried was 26. Can you do with lesser number of assignments? First, I can tell you what is possible answer. We could possibly do with just trying 5 assignments. Look, you have to try at least 4, right? You have to pick, you have to assign. What I mean by an assignment is every time you assign a value to a variable. So there are 4 queens, so we have to assign all of them one value, right? So 5 is not too bad. Let's go back to our example here. So what we are going to ask ourselves is that could we have done with. So here we went and tried to put an place the queen over here. Somehow could we have figured out that we should not place the queen over here? Yeah.
Whenever we place a queen down, like, is there like some way, or like, should we like check the other positions to make sure that they'll also fit down a lot?
Well, yes. So that is of course kind of what we are doing over here right now, right? Like when we place the queen over here, in some sense it is telling that look, you should never place the other queens over here, right? Because what happens in the second queen? We are going to check whether we can place the queen over here. This is not consistent. This is not consistent. So then we ended up and placing the queen over here. One thing is, of course, you can say that, oh, ask someone else. And if there is some more powerful algorithm that can just tell us the solution, right? So we can't ship this to someone else solve the problem. And the reason I'm mentioning is that one thing, as I mentioned to you, that the constraint satisfaction problem just only for the variables take value 0, 1 is this NP-complete problem. So NP-complete problems are the problems for which we don't know a better, in the worst case, we don't know if there's a better algorithm than exponential time algorithm. Okay? So in some sense, these problems can be really, really hard in the worst case. So we do want to come up with an algorithm that can't just say that, oh, solve the problem, and once you tell me the solution, I'm going to figure out whether you can place the queen here or not. Okay? So what can we do here? How can we figure out that we should not be placing the queen over here? Takes the least amounts of cells. What do you mean by that? We try to see what would happen if we were to place it here. But the thing we are asking is that can we do it even before we place the queen over? Okay, so let's try to see what we know so far. So what are we doing over here? When we place the queen over here, then what do we know from no attack of x1 and x2? Given that we place the queen 1, x1 at 1, what do we know? That x2 cannot take value 1 or 2, right? It cannot take. What else we know? x3 cannot take the values 1 and 3. Well, and similarly, x4 cannot take values 1 and 4. So we know that x3 must take value either 2 or 4. If x3 takes value 2, we are not committing to anything. But suppose x3 takes value 2, then what's the value x2 cannot take? If x3 is 2, then what's the value x2 cannot take? Can't take 1, 2, 3, right? Although we already know that it can't anyway take 1, 2. Can't take value 3. If x3 were to take value 4, what are the values x2 cannot take? If x3 takes value 4, then what are the values x2 cannot take? 3 or 4, right? What do we know out of these? Look, x3 has to take one of these two possible values. In both cases, we know that x2 cannot take value 2. Sorry, x2 cannot take value 3. Huh? So that would mean that x2 cannot definitely take value 3, right? Do you see? Because x3 has to take some value. And we know that in either case, whatever value it takes, x2 cannot take value 3. Since now we know that x2 cannot also take value 3, well, in that case, x2 must take value 4. But if x2 takes value 4, then what do we know? x3 cannot take value? x3 cannot take value 4 anymore, right? Oh, sorry. x2 should be 4. Yes. And now x3 cannot take value 1, 3, 4. So let's see. If x3 cannot take value 1, 3, 4, then x3 must take value 2. But if x3 takes value 2, then x4 cannot take value 2 or 3. X3 takes. No, we said that x3 cannot be 4. x2 was 4, and now x3 has to be 2. Because if x3 is 2, then x4 cannot be 2 or 3. Yeah. Four is. Yeah. So what we are doing is that we are deriving from this constraint here. Because x3 is 2, then it implies that x4 cannot be 2 or 3. But if x4 cannot be 2 or 3 and x4 cannot be 1 or 4, then x4 cannot be any of the possible values. So what does it mean? It means that, look, nothing is going to work out. So, and so far we are only committed to one assignment of x1. So we have to go back and change our assignment of x1. Okay. Now, because we are going to place x1 as 2, what do we know? x2 cannot take, what are values it cannot take? 1, 2, 3. And same for x3, we know that it cannot take value 2 or 4. And in case of x4, we know that it cannot take value 2. Can we derive something else? Because x2 will be forced to be 4. So it means that x3 cannot be 3 and x4 cannot be 4. Because x2 will be 4. What else can we derive now? Yeah. What else can we derive now? Well, all of them can just only take one value, right? So at this point, all of them are forced to be that value. That's it. That's the assignment. Yes.
So we do this to like the backtracking search, right? Like, is it less computationally expensive to calculate this? That's needed?
That's an excellent question. So in fact, it depends on the problem. So that's why I wasn't showing the time. So it does turn out that if, let's try to look at a real chessboard, 4 cross 4 is too small. So if we were to run this improved version, then we would try 876 assignments and we would take 800 microseconds. Okay? What happens if we run the inference? Well, we would try only 20 assignments. There will be 12 backtracks, but it would take 1.2 milliseconds, 1200 microseconds. So there's a cost to pay here. But if the problem gets harder, so N queen is a very simple problem. So now let's go back to the problem that was a little harder. Okay, so in this case, it takes 890 milliseconds. If we were to run the improved algorithm, but if you run the inference that we are going to talk about, it takes 4 milliseconds. So if the problem is very simple, then of course it does not pay off to do all these calculations. And that's kind of an important lesson in life. Sometimes instead of thinking too much, you might just want to just try out, right? If the stakes are not high, just try out. But if stakes are high, spend some time thinking about the consequences. And the same thing happens for in our CSP world. If the problem is going to be harder, spend some time thinking, then just trying it out. Yeah, there was a question. Okay, so now let's go back to asking how to design this algorithm. Yeah. Can everyone see over here? So what I want you to do, and this is the algorithm that we are going to design, is under the core of all the solvers out there. This is what makes the solvers work. Took us a long time to discover this algorithm. It's a simple algorithm. We should be able to discover just trying and thinking hard about the 4-queen problem. Okay? So we are just going to today spend some time trying to see how we could come up with the algorithm. And in the next lecture, we are going to look at the algorithm. Okay? So what I'm going to do in next 10 minutes is just again trying to walk over what we did and try to see if there's a pattern in what we were doing that we could have come up with the algorithm. Okay, so let's try again. We started over here. We placed the first queen somewhere. Then what do we want? What we are trying to do? Because we placed the first queen over here, we know something won't hold true for other variables, right? So we go over and we try to mark things we know won't hold true. Then what did we do? And I'm going to mark what we are doing over here so that you remember. So we tried some assignment and then we figure out don't hold for x2, x3, x4, right? Now what should we do? Huh? We wanted to do without assigning x2, right? Yeah.
Like, are you saying what do we do after we find out that it won't hold?
No. Let's go back to what we were doing earlier. We assign over here, we figure out that this won't hold true. Then what did we do next? So we took some constraint, right? For example, we started looking at that, look, the no attack of x2 and x3 tells us that, what did we learn from this constraint, x2 and x3? It tells that, look, because x2 can only be 3 or 4, we deduce that x3 cannot be 4. What did we do here? We pick some constraint. And then based on that constraint, how are we deducing that x4 cannot be 4?
Whichever place you put it in, it will always be lined up with that S4, taking up that space.
Oh, I'm sorry. It should be x3 cannot be 4. Yeah. Sorry, you were saying that. So whichever, so what are we doing? We are saying that, look, for all the values that x2 can take right now, is there some value that x3 can no longer take? Or ask the other way, for a value x3 can take, is there some value that x2 can possibly take? So for x3, 4, we know that x2 cannot take any of the possible values anymore, right? Because x2 cannot take 1 or 2. So what we figure out that, look, when x3 is 4, x2 cannot take any possible values that remain. Right? Because when x3 is 4, x2 could have only taken 2 values right now, 3 or 4. But when x3 is 4, x2 cannot take 3 or 4. So what must be the case? x3 cannot be 4 anymore. Right? Now what do we do now? So we have figured out that x3 cannot be 4. So we had to pick some constraint. How are we figuring out what constraint to pick? What is it about this new information learned that can tell us what constraint to pick? There are many possible constraints. Should we go and look at the constraint of no attack of x1, x4? Yeah. Okay. Can we try to figure out the next constraint to pick based on something that just happened here? So look, we know that x3 cannot be 4, right? So we learned something new about x3. So we can either try to, because we also learned something about x2, so maybe we check the constraint for x2, x4. Or we have learned something new about x3, so maybe we should go and look at the constraint that involves x3 and see if we can learn something more. Because we learned something more about x3, maybe we should look at all the constraints where x3 appears and say, can we learn something more about other variables? So after this step, we could go and say that, look, I want to look at the constraint where x3 appears. There are many constraints, maybe no constraint of x1, x3. In this case, we are not going to learn anything new, right? Because we already figured out x1 is going to be, we assigned x1 to 1. We look at the constraint of no attack of x2, x3. Well, in this case, we can figure out that x2 cannot be, it can't be 3, right? Maybe we also go over some constraint. What other constraint x3 appears? x3, x4. What do we know now? Because we know that x3 can only take one value, right? So is there some value of x4 so that x3 won't be able to take that value? Well, definitely if x4 is taking 2 or 3, then x3 won't be able to take 2. And at this point, this should be alarming because we had already figured out that x4 cannot be 1 or 4. And suddenly x4 cannot be 2 or 3. So x4 cannot take any of the possible values. Yes?
So when we're talking about the constraints, we're only caring about when we're talking between two variables, like between x2 and x3. We look at x2 and possible values we can take, sort of, not really like putting the thing in, checking everything. But we care about how it affects x3, and x3, we only care about the values of x3 that any value of x2 will make, like, so like while x2 does affect, the spot of 2 sometimes, but it doesn't affect it every spot it's in. So we only care about x3 being 4, not belonging. So that's why we don't include 2. x3 can't be 2 at some point, right?
Yes, because that's the important thing that right now we are, no. I mean, we already have figured out that x3 cannot be 1, 3, 4, right? So when we are taking this value, what are we checking? Is there any value of x2 for which x3 can take a possible value out of things that are allowed so far, right? We already know that x3 cannot take 1, it cannot take value 1, 3, 4, right? So we are asking, is there any value of x2 for which x3 can take among the values it's allowed anymore, right? So what we know is that when x2 is 3, x3 cannot take the value. There's only one possible value it has, right? When x2 is 3, x3 can no longer take the value or so, to 2. And that was the only possible value allowed, right? So it means that x2 cannot be 3. But look, and in this case, we are only concerned about this constraint. We have forgotten everything else. So maybe this is kind of enough information to figure out the algorithm that we are going to design, right? Some things we assign, we figure out what we have learned about other variables. Then we go over the constraint where those variables appear. Then we learn something more about other variables. Then we must go over the constraint those variables appear. One thing we definitely want to do is that this algorithm on its own should be polynomial time. So it should not just repeat forever. Right? So you have to figure out how to make sure that this does not repeat forever. And we are going to look at the algorithm next week. Okay, so let's conclude there, and I'll see you in 2 weeks.